You're listening to DTFHN for April 22nd, 2026. I'm your mass-produced artisanal host, Jack Hacksmith. We are your daily tech feed for Hacker News, a website where people who build things argue about whether they should have. Today's a day for beautiful contradictions and elegant stubbornness. Let's get weird. I have enough context from the comments and background knowledge to write this segment. Let me draft it. One commenter put it best. And I'm quoting directly. Jesus fucking Christ, this is an abomination of epic proportions that has no right to exist. And then, in the same breath, announced they were going to run it inside Windows 95 on a Sun PC card under Solaris 7. That's the entire ethos of this project in 2 sentences. Horror, followed immediately by the compulsion to make it worse. Windows 9 X Subsystem for Linux. Read that name again. It's WSL spelled backwards. Instead of running Linux inside modern Windows, Haley Somerville built a system that runs a modern Linux kernel, cooperatively inside the Windows 9 by kernel. Windows 95. Windows 98. The operating systems that crashed if you opened too many folders. The Hacker News thread is a beautiful parade of people who lived through the era recognizing exactly how cursed this is. Several commenters immediately drew the line back to Linux and Flina. Projects from the XP era that let you run unmodified Linux binaries inside Windows by implementing a compatibility layer. Flinex translated Linux syscalls into Windows NT syscalls in user space. Linux ran a modified Linux kernel cooperatively alongside the Windows kernel. Both required NT's relatively sane memory management and process mode. Windows Joe X had none of that. It was a 32-bit shell duct-taped onto DOS with cooperative multitasking held together by hope and IRQ conflicts. The fact that you can get a modern Linux kernel running inside that environment is, and I want to be precise here, technically unnecessary and spiritually essential. Somerville already proved the concept could work in the other direction with DOS Linux, which boots a Linux kernel from DOS. This new project is the logical next step in a progression that no one asked for and everyone needed. Someone in the comments asked whether this could have actually let you run Linux under Windows 95 back in 1995. And the honest answer is, probably not with a modern kernel, but the architecture would have been sound. The tools just weren't there yet. And that's what makes this worth celebrating. This is open source at its most gleefully pointless and deeply instructive. Every piece of this project, the kernel modifications, the cooperative scheduling tricks, the memory management hacks required to coexist with Win9X, is published, readable, forkable. You can study how operating systems actually work at the boundary layer by watching someone force 2 of them to share a single-threaded apartment they were never designed to occupy together. The best engineering isn't always the most practical engineering. Sometimes it's the engineer who looks at 2 incompatible systems and says, I'm going to make these coexist, and I'm going to show my work. I love that this show just goes the places. Next up, someone literally making RAM. At home. Let's get into it. 14 words in a YouTube title. Making RAM at home. Lowercase, matter of fact. Like a recipe video. How to make your own RAM in a shed. Sit with what that actually means for a moment. Dynamic random access memory is one of the most precisely manufactured objects in human civilization. Each cell is a capacitor and a transistor, etched at scales measured in nanometers, replicated billions of times across a single chip. all inside fabrication facilities that cost $10 to $20 billion to build. The clean rooms alone require air thousands of times purer than a hospital operating theater. The lithography machines weigh multiple tons and use light sources that push against the boundaries of physics itself. And someone is doing this at home. The first principles question is worth asking. What does DRAM actually require? Strip away the marketing, strip away the trillion-dollar supply chains. A DRAM cell needs exactly two things: a capacitor to hold a charge representing a bit, and a transistor to gate access to that capacitor. The charge leaks, so you refresh it periodically. That's the entire concept. Everything else is scale, yield, and precision. One of the commenters asked the right question. How do you actually read the value? And how does the refresh cycle work? These are the questions that matter, because they reveal that the underlying principles of computer memory are not mysterious. They are electrical engineering you can reason about, test, and yes, build with your own hands if you are stubborn enough and willing to construct a clean room in your backyard. This channel doesn't just show the finished product. It documents building the fabrication environment from nothing. The clean room, the process controls, the photolithography steps, every piece of it visible, documented, reproducible. This is semiconductor manufacturing, with the walls made of glass. The global chip supply chain is one of the most concentrated systems humans have ever built. A handful of fabs, a single lithography vendor, geopolitical choke points that keep defense strategists awake at night. The default assumption is that this complexity makes the knowledge inaccessible, that you need the billion-dollar facility to even begin understanding how memory works. This project is a quiet refutation of that assumption. The knowledge is not locked inside the fab. The physics is the same at every scale. And when someone publishes their process for building memory from raw silicon in a home laboratory, they are putting tools where others can reach them. The shed is the fab. The video is the documentation. The principles are eternal. This one's pure joy. You use it every day and probably have no idea how wild the physics actually is. In knowing time PPB Dufresne, Korean Airlines Flight 000 Sisblis drifted into Soviet airspace because its inertial navigation system was incorrectly set. The Soviets shot it down. 269 people died. Within weeks, Ronald Reagan signed a directive making GPS available to civilian aviation. The technology existed. The satellites were already up there. The only thing that changed was the policy decision about who got to use them. That history matters because GPS is one of the cleanest examples of what happens when a government builds infrastructure and then actually opens it. The system is free. The signals are unencrypted. Any manufacturer can build a receiver. No license, no API key, no terms of service. 31 satellites maintained by the U.S. Space Force, broadcasting timing signals to every device on Earth that cares to listen. And the underlying principle is almost absurdly elegant. A satellite says, "The time is now." Your phone hears it a few milliseconds later. Multiply that delay by the speed of light, and you know how far away the satellite is. One satellite gives you a ring of possible positions. 2 satellites narrow it to 2 points. 3 satellites collapse it to 1. A 4th satellite exists purely to fix the fact that your phone's clock is garbage compared to an atomic clock in orbit. Because with 4 distance equations, you can solve for 4 unknowns: latitude, longitude, altitude, and your clock's error. The part that turns genuine wonder is the precision stack. 1 nanosecond of timing error equals 30 centimeters of position error. So the system has to correct for everything. Atmospheric drag on the signal, the ionosphere bending radio waves. And then, this is where it gets genuinely beautiful. Einstein, the atomic clocks on GPS satellites tick faster than ground clocks because of general relativity. Weaker gravity up there, time runs differently. If you don't correct for relativistic effects, your position drifts about 10 kilometers per day. Einstein's theories are not abstract physics. They are operational firmware corrections running on every satellite in the constellation. The article from Per36 walks through all of this with interactive 3-dimensional visualizations running natively in the browser. You can ping virtual satellites and watch the rings intersect. The commenters pointed to Bartosz Sikanowski's deeper treatment, which is also worth your time. Pull this thread all the way, and you arrive at something remarkable. The most precise navigation system ever built is free, open, and funded by taxes. No subscription, no premium tier. The architecture is the argument. When you build infrastructure as a public good and let anyone access it, 7 billion people find uses you never imagined. That is how open systems win. Not by arguing the principle, but by being so useful, the principle becomes self-evident. Moving on. 250 trillion parameters devoted to getting your fingers right. That is roughly the scale of what OpenAI just shipped with GPT Image 2. And the thing that floors me is not the output quality. It is the architecture of the problem they had to solve to get there. Think of image generation like orchestrating a symphony. Earlier diffusion models were conductors waving at 100 musicians and hoping the ovosection followed the baton. The new approach, natively multimodal, generating images token by token inside the same model that handles text, is more like a composer who plays every instrument. The model does not hand off to a separate image pipeline. It reasons about what it is drawing while it draws it. Text rendering, spatial layout, the number of fingers on a hand. These stop being failure modes and start being solvable because the system can think about them the way it thinks about a sentence. The results are genuinely impressive. Prompt adherence is sitting around 70% on rigorous benchmarks, neck and neck with Google's latest, both of them leaping past what was possible 18 months ago. One commenter built a structured heuristic test. Domain-specific prompts requiring real knowledge, not just aesthetics, and reported the model actually reasoning through the constraints before generating. That is new. That is the text and image reasoning loop doing real work. Simon Willison, as usual, had a working script published within hours. 14 lines of Python. Publicly shared, immediately usable. That is builder culture at its best. Someone sees a new capability and their first instinct is to make it accessible. Now here's the tension worth naming. This is a closed model behind a paid API. The capability is extraordinary, but the architecture of access is familiar. One company, one endpoint, one set of usage policies deciding what you can and cannot generate. Meanwhile, open models like Flux and Stable Diffusion 3.5 keep closing the gap. They are not at parity yet on prompt adherence, but they are on a curve. And crucially, they run on your hardware under your rules. The craft here deserves genuine admiration. Fusing text reasoning with image generation at this fidelity is a serious engineering achievement. But the most interesting question is not whether the output looks real. It is whether the next model that matches this quality will be one you can download, modify, and run without asking permission. History says yes. The open ecosystem has a habit of catching up. And when it does not charge per pixel. That's irritating after Untitled Chapter. Reply as hapimen to dad dal really door. Cold the pride braching detail. Extended after. Card. Coloreversion do lateral mange leo. By cobble, way, don't opt, you're really to. Just named and left for the listener to sit with. 5 stories in, and we haven't even gotten to the one that might actually change how you work tomorrow. Let's fix that. Every distributed system I have ever built eventually hit the same wall. You design for request response, and then someone asks what happens when the other side is not there. That question breaks everything. This is exactly where AI agents are right now. The entire ecosystem grew up on a simple loop. HTTP request carries the prompt in server-sent events, stream the tokens back out. It works beautifully when a human is sitting there watching. It falls apart the moment the agent outlives the connection. And agents are outliving their connections everywhere. Cron-triggered routines, background code agents running in the cloud. Scheduled tasks that fire at 2 in the morning and need to tell you what they found. The article catalogs the usual suspects. Anthropic has channels and remote control and scheduled loops. Cursor has background agents. ChatGPT has scheduled tasks. The pattern is universal. The transport is not. Run this forward 3 years. Your development environment has 6 agents working concurrently. 1 is refactoring a module. 1 is monitoring your staging deployment. 1 is reviewing pull requests from other agents. A 4th is blocked on a human approval step and needs to reach you on whatever device you happen to be holding. The HTTP request response model cannot express any of this. You need durable messaging. You need presence. You need push semantics that survive disconnection and reconnection across devices. One commenter nailed it. The problem is not HTTP itself. It is the industry's fixation on concatenating messages into a single conversation stream. The conversation metaphor was useful scaffolding. It is now the constraint. The interesting detail is what is emerging underneath. Temporal workflows, event-driven architectures, pub-sub patterns that distributed systems engineers have used for decades. The agent infrastructure problem is converging with the distributed systems problem, and the solutions look remarkably similar to the ones we already have. The question that matters is whether this infrastructure calcifies into proprietary platforms or crystallizes into open protocols. Right now, every major player is building their own async agent runtime. That is the moment where open standards either emerge or do not. The plumbing is less glamorous than the models. It is also more consequential. Whoever owns the transport owns the topology of what agents can become. We talked about building blocks earlier. Here's one that's pure joy. MuJoCo just leveled up its physics simulation. Let me make the case against trusting this. Google DeepMind open sources their physics engine, and the rational response is suspicion. A trillion-dollar company does not give away strategic infrastructure out of generosity. They do it because an ecosystem of researchers training robots in MuJoCo feeds discoveries back into Google's pipeline. Every PhD student optimizing locomotion policies is, in some sense, doing unpaid R&D for Mountain View. The cynicism writes itself, and it is wrong. Here is why it fails on its own terms. MuJoCo's codebase is C, not a hosted service, not an API with a billing page, not a platform that phones home. You download it, you compile it, you run it on your own hardware. One commenter in the thread is training a G1 humanoid robot and specifically celebrates that they do not need to fight with NVIDIA's software stack. It runs on macOS. That sentence contains more liberation than most corporate open-source announcements manage in a full press release. The engineering deserves specific admiration. MuJoCo's simulation module operates on pre-allocated low-level data structures compiled from XML. That is a deliberate architectural choice. Pay the cost upfront at parse time, so the runtime loop stays ruthlessly fast. Contact dynamics with articulated bodies is one of the hardest problems in computational physics. Joints introduce constraints. Contacts introduce discontinuities. Doing both accurately and doing both fast is a genuine achievement in numerical methods. The MJX branch rewrites the physics step in JAX, which means you get analytical gradients through the entire simulation. You can differentiate through physics. Train a locomotion policy, not by reward hacking through millions of random rollouts, but by following the actual gradient of the actual dynamics. That is elegant. The question nobody in the robotics community wants to sit with is this. If the simulation layer is open, and the training frameworks are open, and the hardware is increasingly commoditized, what exactly is the moat for any robotics company? The answer might be that there is no moat, and that is the point. Someone built a racing simulator with it. Someone else simulated a mini-golf course for a YouTube video. A research lab is teaching a humanoid to walk. Same engine, same open code base. This is what happens when you put physics where people can touch it. The use cases do not converge. They explode. DeepMind's motives can be as strategic as they want. The code is already out. The gradients are already flowing. And 1,000 builders who had never gotten access to a simulation engine this good are already using it to teach machines to move through the world. The genie does not go back in the bottle, and in this case, the genie does contact dynamics at 60 frames per second. Rust's whole promise is memory safety, and someone just made its garbage collector live up to that promise. What if the safest way to manage memory is also the most annoying way to manage memory? This is a question that has haunted language designers since at least 1960, when John McCarthy's original Lisp garbage collector freed programmers from manual allocation and immediately introduced an entirely new category of performance problems. 64 years later, Nick Fitzgerald asked a version of this question specifically about Rust. And the answer he got is both satisfying and deeply, characteristically, Rust. Here is the setup. Rust's entire personality is built around ownership and borrowing. You do not get to have two mutable references to the same data. The borrow checker enforces this at compile time. Garbage collectors, by their nature, need to do exactly the thing Rust does not want you to do. Reach into memory, decide what is alive, reclaim what is not, all while other references might still exist. Every previous GC library for Rust accepted this tension and used unsafe code internally. Safe on the outside, unsafe on the inside. A chocolate-covered pretzel of memory management. Fitzgerald's Safe GC crate uses zero unsafe code, none in the API, none in the implementation. A forbid unsafe code pragma sitting right at the top of the file like a no shoes, no shirt, no service sign. The trick is almost disappointingly elegant. Instead of letting you dereference a GC pointer directly, you index into the heap. You hand the heap your pointer. The heap hands you back your object. Every access goes through Rust's normal borrow checker. The heap owns everything. You are just visiting. The trade-off is ergonomics. You cannot just dot into a field on a GC reference. You have to carry the heap around like a hall pass. The trace trait that tells the collector about object references is safe to implement, which means if you forget an edge, you get a memory leak instead of a use after free. Leaks over crashes. That is a trade most people will take. The Hacker News comments land exactly where you would expect. People noting the ergonomic cost, people wondering about performance, someone inevitably bringing up CVERS. But the proof of concept stands. You can build a garbage collector inside Rust's safety model without ever escaping it. The compiler is the straitjacket, and someone just did a cartwheel in it. Not a fast cartwheel, but a correct one. We have covered a lot of ground today. Let's close with something that genuinely made me smile. The fundamental engineering problem with the human eye is that it is a pressurized system you cannot easily instrument. Glaucoma damages the optic nerve through elevated intraocular pressure, and the gold standard for measuring that pressure requires a clinic visit. Often months apart, you are sampling a continuous dynamic process with a handful of snapshots per year. That is like diagnosing a heart condition by checking someone's pulse twice in January. Previous smart contact lenses tried to solve this by embedding electronics directly onto the cornea. The FDA approved one called Triggerfish back in 2016. And here is where the devil's advocate argument gets interesting. Electronics give you the most precise measurements, full stop. If accuracy is all you care about, rigid sensors win. So why walk away from the best tool? Because the cornea does not care about your sensor's precision. If the patient stops wearing the lens after 3 days, rigid electronic components against delicate corneal tissue cause irritation, and the compliance data on glaucoma treatment is brutal. Nearly half of patients abandon their medication within 6 months. The most accurate system in the world is worthless if it sits in a drawer. The team at the Terasaki Institute built something different. An all-polymer lens with no electronics at all, microfluidic channel. Tiny passages molded into the lens using 3D printed forms. Replace every electronic function. A red fluid in a snaking channel gets pushed further as eye pressure rises, readable by a phone camera and a convolutional neural network at 94% accuracy. That is the sensor. For drug delivery, pressure-activated reservoirs compress as intraocular pressure builds, pushing medication through channels whose width determines the activation threshold. Levittoprier's threshold. 2 reservoirs, 2 drugs, 2 different pressure triggers. A closed-loop treatment system with no battery, no circuit, no rigid component touching the eye. The silk sponge inside those reservoirs absorbs 2,700 times its weight in fluid. 2 weeks of medication in a soft lens. The patient does nothing. The physics does the work. This is what good engineering looks like. Not more technology, but the right technology shaped to how humans actually behave. We talked earlier about systems that do more with less. Story 9. Laws of software engineering. One commenter just nailed it. End quote. What do you call the law that you violate when you vibe code an entire website for list of laws of software engineering instead of just creating a Wikipedia page for it? That is the most efficient code review I have ever seen. 1 sentence. No pull requests necessary. Somebody built a whole site. Beautiful layout, little icons, smooth animations. To list principles that mostly tell you not to build more than you need. Yagni is right there on the page. You aren't going to need it, sitting next to the carefully designed card grid that you absolutely did not need to carefully design. The irony is structural. But pull this thread a bit and the comments get genuinely interesting. Multiple people pointing out that these laws contradict each other. The Boy Scout rule says leave code better than you found it. Yagni says don't add anything until it's necessary. Premature optimization says stop trying so hard. And one commenter, clearly someone who has shipped production code that caught fire, pushes back hard on the glow quote, arguing that premature optimization is the root of all evil, has become a thought-terminating cliché, an excuse not to think about performance until the architecture is already locked in and it's too late. They're right, and this is the bootstrapism angle that matters. These laws aren't scripture. They're heuristics that became bumper stickers. The danger is when organizations treat them as policy. When don't optimize prematurely becomes never talk about performance in a design review, or when Brooks's law becomes an excuse to never hire. The value of listing them together like this is that the contradictions become visible. You can see that software engineering doesn't have commandments. It has tensions you navigate with judgment. Linus's law is the one that earns its place on the wall. Given enough eyeballs, all bugs are shallow. That is not a platitude. That is an architectural argument for open source. The law that actually scales. Meta employees are discovering what it feels like when the training data is you. Look at the name they chose, Model Capability Initiative, MCI. 3 letters that sound like an internal infrastructure project, not a system that records every keystroke and mouse movement of 100,000 employees. That naming choice tells you everything about how this was designed to land. Here's what's actually happening. Meta is installing software on every U.S. employee's work computer that captures keystrokes, mouse movements, click locations, and screen content. The purpose is training AI agents to use computers the way humans do. Choosing from drop-downs, using keyboard shortcuts, navigating interfaces, and the engineering goal is genuinely interesting. Teaching models to operate software by watching real workflows is one of the hardest problems in agent development. The training data has to be messy, varied, authentic. You can't synthetic generate someone's actual Gmail workflow. The employee reaction was immediate. The top-rated comment on the internal announcement was, "How do we opt out?" CTO Andrew Bosworth responded directly, "There is no option to opt out on your work-provided laptop." The angry face emoji was the most common reaction. Now run the open-close test on this system. Who controls the data pipeline? Meta. Who decides which applications get monitored? Meta. Who determines what counts as a privacy safeguard? Meta. And critically, who benefits from the trained models? Meta's proprietary AI stack. This is a closed training loop. 100,000 knowledge workers generating behavioral data that feeds models they will never own, inspect, or redistribute. The engineering is admirable. Capturing real computer-used patterns at scale is exactly the kind of data that makes agents actually useful. But architecture determines outcomes. If this data trained open models that every developer could build on, you'd have a bootstrapping engine for human-computer interaction research. Instead, it trains proprietary models behind a corporate wall. The workers generate the value. The corporation captures it. The craft deserves better infrastructure than that. This has been your daily tech feed for Hacker News for April 22nd, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voice by Qwen3 TTS. Not affiliated with Hacker News or Y Combinator. Now go build something worth sharing. We'll see you back here tomorrow.